All right, chemists, we're going to start a new unit in this lesson. This is all about thermochemistry and phase changes, and what you see in front of you is an example of what's called a heating curve. This plots temperature versus time, and it shows us the different kinds of changes, in this case physical changes, that happen as we take some sample that's originally a solid and convert it into a liquid, and then eventually a gas if we apply enough heat to that. So this is a plot of temperature on the y-axis and time on the x-axis. And what we're going to do is learn how we can use these types of heat changes to indirectly measure properties related to heat energy for other types of chemical changes. So the first problem says, what's the total heat required to bring some mass of water that's 1 mole from an ice cube below its freezing point to gaseous steam well above its boiling point? And for that, we need to annotate this graph a little bit more and show what's going on. So let's assume we're down here in the solid region, and it's originally 30 below 0 Celsius where we start. And then if you trace this, you can see you undergo a temperature change. So this is just heating up solid ice until you get to this plateau. And the plateau is the phase change. And we should know that at atmospheric pressure, ice melts at 0 degrees Celsius. So that takes some amount of energy to heat it up, and then some separate amount of energy to melt it. So above where it says B, that's melting. And then you get to this line segment C. C is heating up the liquid water, which we go all the way from 0 up to, this must be 100. I don't think this y-axis is a scale, but that's okay. It's just to give you an idea of what's happening as the changes occur. And then you get to, at 100, you get to a second plateau. It's no coincidence that it's a lot lengthier than what we had originally. This is boiling or vaporization, when you go from the liquid to the gas phase. And then once every molecule is gaseous, you're heating up the steam until you get to some temperature that they're asking us about. I think they said 140. So there's 5 different segments that we can talk about here: the heating of the ice, the melting of the ice, the heating of the liquid water, the boiling of the liquid water, and then the heating of the gaseous steam. And that breaks it down into 2 different types of physical changes. There's a heat related to a temperature change, and that's proportional to how much of the substance you have, its mass, what's called the specific heat of the substance, which is a property related to what that substance is. We abbreviate it with C. And then the change in temperature. So the more you change something's temperature, and based on what that substance is and how much of it you have, tells us how much heat is related. That's 3 of those sections. That would be A and C and E. The other 2 that are for phase changes are just based on how much of the substance you have, M, or N, depending on if you want mass or moles, times what's called the latent heat, which is the delta H for whatever phase change it is, melting or boiling or what have you. So Q for a phase change is mass times delta H. So we're going to use these 2 equations today, both directly and then indirectly, to look at the heat that can be absorbed or released by a quantity of water, and we'll use that to indirectly figure out heats related to other things. So first, let's just show how we use those. So how much would it require to take a mole of water from a solid ice cube to gaseous steam? And here's all the constants that we need already given to us. So there's going to be 5 terms: that heat related to segment A, B, C, D, and E. And they can add together, but I'm going to write them out separately. So segment A is a temperature change. So it's the mass, 18 grams, times the specific heat of ice, which is 2.03 joules per gram degree Celsius, times the delta T. Delta T is always final minus initial. It's always where you are at the end minus where you just were. So our final temperature for segment A is 0, and our initial is minus 30, So 0 minus negative 30 is actually a positive delta T of 30. Don't get the signs confused. You'll get incorrect numerical values. So 30 degrees Celsius. You can see here units take care of themselves. Grams cancels with grams. Celsius and Celsius, you're left with joules. What about segment B? Segment B is a phase change. That's the melting. So I'm going to use this second equation. It's still 18 grams. And the latent heat of fusion is this second term. That means for melting or solidifying, it's actually positive in one direction and negative in the other, but the magnitude is the same. So this is 334 joules per gram. And then for the other three terms, we have the heating of the liquid water. It's still 18 grams. Liquid water has a specific heat of 4.18. And the delta T from 0 to 100 would be 100. For boiling that 18 grams, it would be 18 times the 2259 that I see over there for the latent heat of vaporization. And lastly, to heat up the steam, 18 times the specific heat of steam times the remaining 140 minus 100, 40 degrees. And you just add those up and you'll get a numerical value, Q total, of quite a big number. It should be 56,748.6 joules if I don't round anything. I'm going to round that and convert to kilojoules because it's such a big number. You get 56.7 kilojoules. So that's just to show that they add together, and that's how we use those two equations. Now, why do we care about this for a chemistry class? Well, since we know so much about water and what it takes to change its temperature or to change its phase, we can use it to indirectly figure out how much heat is related to other processes, whether it's a physical change or a chemical change. This is called calorimetry, because we're actually measuring metric, something related to heat, caloric. And we can do this to find properties of substances or how much energy is involved in a chemical reaction. For example, here we have some mass of a metal, and it's initially quite warm at 75 Celsius. I put it in cold water, and the mixture heats up to some final temperature, and I want to know what's the specific heat of the metal. Well, I put this generic equation up here that says Q1 plus Q2 plus Q3, etc. is equal to 0. This is essentially a conservation of energy equation. Conservation of energy. So we have the heat related to whatever system we're studying, plus the heat related to whatever its surroundings are, is equal to 0. And that's always true. That's essentially what that equation right there says. This is actually to highlight that sometimes you have multiple systems happening or maybe multiple surroundings, but this one's just two things. We have a metal cooling down and we have water heating up. Those are both temperature changes. So I'm going to use MC delta T of the metal plus MC delta T for the water, and set that equal to 0. And we know almost everything in these equations. I have 150 grams of the metal. I don't know its specific heat. That's my unknown. The delta T is the final minus initial. What's the final temperature of the water? Of the metal? It's actually the same as the water, because you can imagine mixing the metal and the water. They're going to equilibrate to some final temperature. So the final of 18.3 minus the initial temperature of the metal 75.0. And that'll give me my heat related to the metal, but my unknown is buried inside at the C value. What about my surroundings? The surrounding is the MC delta T for the water. So we have 150 grams of water. The specific heat of water is 4.18. And the delta T of the water is the final minus initial of the water. So 18.3 minus 15.0 equal to 0. So we have one big numerical equation and one unknown. Just a concept check. Notice that the metal is cooling down, so this is actually a release of heat. This would be a negative number. The water is heating up, so this would be an absorption of heat. This would be a positive number, and they cancel each other out and equals 0. So you do the math, you solve for C, you get a decimal. You get about 0.24 joules per gram degree Celsius. No surprise, metals have very small specific heats compared to things like water. Water has a notoriously high specific heat. It takes a lot of energy to heat up water, and it takes very little energy to heat up a piece of metal. You know this if you've ever cooked, and you've noticed on a stove, a metallic pan is going to get hot long before the water inside of it, because the water has such a higher specific heat. So that's how we use water to indirectly measure the heat or a property of some substance that's inside of it. We can do this for reactions as well. Let's say we do a precipitation reaction of barium and sulfate in some amount of water, and I want to know what its change in energy is, or its change in enthalpy. So I use the same starting equation, Q system plus Q surroundings is equal to 0. My system is actually the reaction, and the heat of a reaction actually is going to look similar to what we saw for the heat of a phase change. It's not a phase change, it's a reaction, but it's related to the change in enthalpy of that reaction, delta H, and then that's times how many moles of reaction we have. I'll explain more what that means in a moment when we see what that looks like. And then I add this to the surroundings. The surroundings is the reaction mixture. In this case, it's the water and then plus these originally soluble compounds that get mixed in. So we're going to have a temperature change of the resulting solution. So I can just write MC delta T. So then that means my N delta H is equal to negative MC delta T. And that's negative. What's our mass? Well, we have 2,000 grams of water, but I also am mixing with it a mole of sodium sulfate and a mole of barium nitrate. And if I just look up in my periodic table, I need some molar masses. A mole of sodium sulfate weighs 142 grams per mole, and a mole of barium nitrate weighs 261.33 grams per mole. So since they're getting combined, I actually have to add those masses. Masses are additive, so I have 2,000 for the water plus 142 for the sodium sulfate, and then another 261.33 for the barium sulfate. Maybe you can label those if that helps. That's for the water, that's the sodium sulfate, and that's the barium nitrate. And it says in the question, assume that the specific heat of the solution is the same as that of water, so 4.18. And the reaction heats up. It goes from 25 to 28.1, so final minus initial looks like 3.1 degrees Celsius. And it looks like I have two unknowns, N and delta H equal to all these terms. But let's go back and think about what reaction is actually happening. The reaction that's happening is barium ion plus sulfate ion turns into barium sulfate. And we have a mole of each reactant. We have 1 mole of barium and 1 mole of sulfate, so they're simultaneously both limiting. So if I consider my 1 mole of barium ion, we use what's called a mole of reaction to define one of these species, and it's just a way of incorporating the coefficient ratio, which in this case is 1, actually for both reactants, and they're both limiting. So you actually have an N of 1 mole of reaction in this case. That's your N right there. So N is just 1. So if I go back to this, delta H becomes the negative of all of this algebra right here, all this arithmetic right here, and it turns into, after you turn it into kilojoules, you get negative 31 kilojoules. And then it's per mole of reaction. If I had a different amount of these substances, I would use that different number right there. And if my coefficients were not 1 to 1, then n would not be 1. So sometimes n is a little bit more involved than what it is right here. I intentionally am choosing 1 just to make it easy to introduce that concept of a mole of reaction. It's also worth mentioning one other thing here. This delta H being negative implies that we have what's called an exothermic reaction. And you can tell because it means the surroundings heat up. That's always true. We can't directly measure the system. We get information about the system by indirectly measuring the surroundings. That's always true when we're talking about thermochemical processes. Okay, let's try one more. Actually, what I'd like you to do is hit pause and see if you can figure out this last one. It says here we're making a solution, but you can think of it as the same thing as you did for a reaction. They actually give you the heat of solution, so they're making a solution by dissolving calcium chloride, which becomes calcium ion and 2 chloride ions, and that has a delta H of negative 81.3 kilojoules per mole or per mole of reaction. Using that delta H value, the amount of calcium chloride, the amount of water, the initial temperature, what's the new temperature going to be? So see if you can use the kind of things we did in the previous problem to solve for that new temperature in this last one. Okay, so let's see how you did. I'm going to start with the same generic expression, Q system plus Q surroundings is equal to 0. And I got to think about what's happening here. Well, we have the dissolving of calcium chloride, but I'm going to treat that as a reaction. So I'm going to write N delta H for the system, and then MC delta T for the surroundings, and my unknown is sort of buried inside the delta T. Now this one doesn't have an N of reaction of 1. This is going to be based on this 10 grams of calcium chloride, whatever that is. So I have 10 grams of calcium chloride. Obviously I'm going to first turn that into moles. There's 1 mole of calcium chloride per 111 grams calcium chloride. And then before I could use the delta H value, I have to look at this reaction. Well, the coefficient of calcium chloride is 1. So there's 1 calcium chloride, or 1 mole of calcium chloride, for 1 mole of reaction. Maybe that's redundant and you didn't put that there, and that's so okay if you can recognize that it is just a 1-to-1 ratio. But I like to, because then I can see how the delta H is used. Negative 81.3 is negative 81,300 joules per mole of reaction. And that's my first term. And if you look at it, the units work out exactly the way you want. Grams, grams, moles, moles, moles reaction. We are in joules. So if I use my MC delta T, there's a whole other term here, plus M. This time the M is the sum of the two, because once again we're mixing it. So 10 grams plus 50 mils, I'll assume that that's 50 grams. So that's become 60 grams times the specific heat of the solution, 4.18 joules per gram degree Celsius. And then the delta T is final unknown minus initial 25. And that whole thing, that entire term that we just wrote there, is what I have to set equal to 0. So at the very end, I just say equal to 0. And I can also check my units, grams, grams, Celsius. And then I didn't write it, but this is Celsius. So we have joules. So joules plus joules works out. If I didn't convert my delta H, I would have to, so that the joules become compatible. So I get one big equation, I do the math, I solve for T, you get 54 degrees Celsius. Concept check, the delta H is negative, so this is exo as before. which means the surroundings definitely heats up, and indeed it does. Calcium chloride notoriously dissolves very exothermically. Okay, so those are a couple examples of how we use calorimetry, which is using the surroundings to indirectly measure the heat of a system. We can use it to get the heat of a solution, the heat of a reaction, or the specific heat of a metal, and it's all about knowing these two equations and how we can use properties of water to indirectly measure those.